Now, today's topic is again the nonlinear programming problem, but we have done enough with the unconstrained optimization problem. Now, that was the simplest form of a nonlinear programming problem where there was no constraint at all, but now we are moving to the situation where we need to optimize the objective function under certain restrictions. That is why we would say the name of this topic as a nonlinear programming problem with constraints. But you know, the constraints can be of two types. The constraint can be of it can be linear, it can be nonlinear. This way it could be two types. Otherwise, we can have two types of constraints with respect to the sign of the constraint. That is either the constraint is of equality type or the constraint is of inequality type. Inequality can be less than equal to and or greater than equal to, but equality means equality. That is why if we just draw the feasible space for the equality constraint, you might be understanding that the constraint would be the feasible space would be only will be considered the boundary of the space, not the inner space will be considered as a feasible space. But if we consider the less than equal to or greater than equal to, then either of the side of the feasible, the boundary of the region will be considered. All right. Let us, today my topic is nonlinear programming with equality constraint. I will show you what does it mean geometrically. Then I will show you how to handle, rather how to get the optimal solution for that kind of nonlinear programming problem. One thing is that in nonlinear programming there is no, you must have been realized that there is no unique methodology to handle the nonlinear programming that you have experienced for linear programming. There was simplex algorithm, in one go you will get the optimal solution. In every type of problem you can apply the simplex algorithm, maybe of the normal simplex, revised simplex, dual simplex, whatever it is, the advanced form of simplex algorithm, but these are the simplex methods. But you must have realized in the unconstrained nonlinear programming problem there are several kind of methodologies available depending on the situation, rather whether the function is quadratic, function is non-quadratic, function is discrete, function is continuous, depending on different situations, whether the function involves single variable, multivariable, all depends on that. Several methodologies are available. These are the tools available for us, and according to our requirement we use it. Now, here again another kind of nonlinear programming problem. Now, you are learning the process to handle nonlinear programming problem in different situations. Okay, that course is offering you that kind of knowledge so that you can apply in your practical area. All right. Now, equality constraint, and equality constraint means simple equality constraint. That is why we can say the general multivariate nonlinear programming problem where the variable is defined in Rn in n dimension, and there is a set of equality constraints. There are m equality constraints, n number of variables. All right. What does it mean geometrically, rather graphically? I will show you. Now, there is a problem for you. Minimization of 2x1 plus 3x2 subject to x1 square plus x2 square is equal to 1. What did you see? There is a constraint to this optimization problem. There is one objective function. Fortunately, the objective function is of linear type, so that you can visualize that space in a better way. It can be nonlinear as well, but the constraint is nonlinear and it is circle, simple circle. It is a circle centered at 0, 0, radius is 1. All right. Now, if I can draw the feasible space as a simple boundary of the circle. All right, and the objective function is moving in the x1, x2 region freely. There is no restriction for x1 and x2. All right. That is why, let me see, it has been said the objective function is a straight line which is having a slope of -2/3. Now, where is the minimum? Minimum will be the point where the lowest line still touches the circle, because the line is moving freely. I will show you the figure. And what is the maximum? Maximum, the line is moving through the space and it will touch to that point where the, if I just go beyond to that, I will be out of the feasible space. What does it mean? I will show you. This is my problem. That is why x1 direction, x2 direction, this is the feasible region, that is the region is only the yellow line. Inner line is not included because the sign is equality type, there is no less than equality, alright. Now, there is a line where fx is equal to 0, this is the value of fx at point 0, 0, this is moving freely here. If this line is moving this way, functional value of that objective function will maximize, and if it moves this way, then the functional value will be, the value will reduce. Okay. Now, for minimization always it will go this way, for maximization it will go that way, that is for sure. That is why in other way we can say that the gradient of the line is positive, increasing this way and decreasing this way, alright. That is why you see this is the minimum for us, because if I go beyond to this point, then I will be out of the feasible space, and that would be the minimum point. I did not to explain this part because you must have done the graphical solution of linear programming. Here is the same way, only difference is that feasible space is non-linear in nature. And where we will get the maximum value we will get here. Because of this symmetricity of the space, we are getting the functional value as 3.6 here and here minus 3.6, alright. Now, there are certain properties of this whole fact. What is the property of this? Just to think the gradient direction of the constraint set and the gradient direction of the objective function. This is the gradient direction of the objective function this way, and this is the reverse direction, reverse gradient direction. For the constraint, what is the gradient direction? Gradient direction will be, if I consider this point, that will be a point. At that point, if I just draw a tangent, normal to that tangent outside would be the positive gradient direction at that point. Okay. Similarly, if I just move through the whole boundary of the circle, at each point we will get a gradient direction, that will be nothing but the rays. These are emanating from the circle outside, alright. These are all the gradient direction. With this idea, just see a nice fact in the next, that if I say very verbally, it is being said that gradient of objective function is a straight line pointing toward the direction of increasing objective function, and the constraint would be the pointing out from the circle, its direction will depend on the point at which the gradient is evaluated. That way I can say, if this is the circle, at this point this one, this is the gradient, this is the gradient, that should be the normal. This is the gradient, this is the gradient, this way. Understood? Okay. Now, for the same figure, the fact you see, this is the circle, this is the maximum value, gradient direction is this one, grad f. This is the minimum value. Where is the gradient direction? Gradient direction of the objective function this way, but at this point the constraint is this way. What did you see? What the fact you got from here, that at the minimum point you must be seeing that the gradient of constraint and the gradient of objective function just opposite to each other. Did you see? And what about at the maximum value? At the maximum value, gradient of the objective function and the gradient of the constraint is in the same direction. It will happen. This is the very nice fact for nonlinear programming. any nonlinear programming problem always is in the minimization problem. This is the gradient direction of constraint, this is the gradient direction of object. Always it will make 180 degree, but here it will make the 0 degree. Okay. We will use this fact, we will revisit this fact in the next, when we will study the next level of Kuntaker condition. There also we will just reconfirm this fact. That is why if we just conclude from here that at the minimum point del f and grad g are parallel but opposite to each other, and the magnitude of gradient vectors is generally not equal. Certainly that depends on the point on which we are calculating the gradient, and at the maximum point both are parallel in the same direction. Okay. Now, if this is the fact, how really we can consider a multidimensional nonlinear programming problem by using this gradient vector, and we want to solve a constrained nonlinear programming problem. We will use this fact. How we can use it? We know the general classical optimization technique, that if we consider the necessary condition first order derivative is equal to 0, and in case of multidimensional case we say the grad f is equal to 0, that is the vector which consists of first order partial derivatives of the function with respect to different variable, that is equal to 0. And what about the sufficient condition? For the sufficient condition we are going to the second order derivative, and that is why there is a concept that is called the Hessian matrix. We form the Hessian matrix in this way: del 2f by del x1 square, del 2f by del x1 xn, this way, that is the n by n matrix, alright, square matrix, and depending on the property of this Hessian matrix we declare whether the sufficient condition, whatever extreme points we, rather the stationary points we got from the necessary conditions, at those points whether it has, the function has minimum or maximum or the saddle point. This fact you already know, alright. That is why what are the facts? It says you that if we see the Hessian of the matrix is positive definite, then it has the local minimum. But again the positive definite matrix, what is the meaning of it? There is a matrix. Now we will say that is the positive definite matrix if all the principal minors of the matrix, these are all positive, or in other way we can say that if the eigen values of that matrix are all positive, then the corresponding matrix is positive definite matrix. That is why at the local minimum point, if x star we got it from the necessary condition that grad f x star is equal to 0, and if we see the Hessian matrix value at x star is positive definite, then we will say local minimum. If the Hessian matrix is negative definite, we will say the local maximum, and if we see the principal minors are few are positive, few are negative, and there is no pattern to it, okay, then we will say for the point at that point function has neither maximum nor minimum. But still there is certain condition we say, if we see the Hessian matrix value at the determinant value is 0, then the function maybe has a local minima or maxima or saddle point, because we need to go for the third order derivative of the partial derivative of the function. But if we see this value is not equal to 0 and but there is no pattern to it, we will declare there is no optimum value for it. This the detail of it I will explain you later on, but with this fact, with this gradient of the function, how it is being used for the nonlinear optimization problem, I will show you in the next. Now let us consider a nonlinear optimization problem where the nonlinear functions are twice differentiable. If these are not twice differentiable, we cannot check the sufficient and the necessary and sufficient conditions, because Hessian matrix needs that it must be differentiated twice, alright, that is necessary condition for us. And there are two methods available for solving nonlinear programming of equality type. One is the method of direct substitution, and the second method is the method of Lagrange multiplier. Today I have a plan to explain you the basics of Lagrange multiplier method. Okay. Now, and the method of direct substitution is a simple one. Let me just go through quickly of this method. One by one, let me consider this direct substitution method for a nonlinear of this type. Alright. Always you need to consider E must be lesser than N, then only the problem is complicated. If M is equal to N, problem is very simple for us. We will get exact number of points and we will get the optimal solution very easily from there. And method of direct substitution, what we do, if I just say verbally, it says that M relations are there, N variables are there, you replace M relation with N minus M variables. What does it mean? Just I am taking one simple example here. This example is having three variables, one objective function, one constraint. Okay. From the constraint, what we will do? We will make one variable in terms of N minus M number of variables. N is here 3, M is here 1. That is why Z can be represented in terms of X and Y. You can represent X in terms of Y and Z. You can represent Y in terms of X and as you wish. Okay. Once we get to represent it, what we will redefine the objective function this way. Once we are redefining the objective function by substituting the value of Z here, and what is the problem is coming ultimately? The problem comes as an unconstrained optimization problem for me. Okay, that is a very simple. That is why the method is the simplest method of direct substitution. But this method fails when this constraint is of complicated type. You cannot make one variable in terms of other two variables. After substitution, the function may become a very difficult function. There this method fails. For the simple cases, this method works very nicely. Alright. Now, if this is the case, just consider as an unconstrained optimization problem, go for the necessary condition, go for the sufficient condition and you get the solution for it. These are the extreme points that we could get from the necessary conditions, because unconstrained optimization problem was having two variables. That is why this is the grad f values. If we just equate to 0, then we are getting the extreme points, but the sufficient condition has to be checked through the Hessian matrix. Hessian matrix construction, it is not a difficult for us. We will simply calculate the Hessian matrix this way. Just look at the matrix, Hessian matrix. The principal minors are, the first principal minor is 5 by 2 positive, second principal minor would be, the value would be 5 by 2 into 5 by 2 minus half square, and the values are coming as one is 6 and the other one is 5 by 2. Okay. Both are positive. That is why we can declare that we are getting a positive definite Hessian matrix. That is why whatever extreme points we got it from the necessary condition, that gives us the minimum value of the objective function. Okay. Now, similarly, we can search for the, if at all exist, for the maximum value. This is the simple method of direct substitution, but there is another method that is a very popular method, that is called the method of Lagrange multiplier. The new thing of this method is that the name has come from the mathematician by the name of Professor Lagrange. From here it has come. We are formulating one Lagrangian function for the given optimization problem by using the Lagrange multiplier, and after that let us see what is happening. And for this problem again we are considering same kind of problem. Let us consider the simplest case. Two variables are there, one simple equality constraint is there, because if there are more number of equality constraints, some complications are arising out of it, that I will discuss in the next class. Today I am considering the simplest case of Lagrangian multiplier method, where only one constraint is there. From here we can construct a Lagrangian function by using a Lagrange multiplier. Lagrange multiplier is, we are considering as a parameter the value of the parameter is unknown to us beforehand, but this parameter will help us to detect whether the optimal solution we got, that is a maximum or minimum. That is the beauty of that Lagrange multiplier. There is a physical significance of the Lagrange multiplier. I will come to that point after explaining the methodology in detail. Now, this is a problem. How the Lagrange function is being formed this way. Lagrange function, if we just introduce one variable lambda, then the Lagrange function will become a function of three variables x1, x2 and lambda. What is that? That would be is equal to f plus lambda into g minus b, because g minus b is being considered as a from the constraint only. Alright. Now, what we have to do? We have to minimize this Lagrange function. Now, whatever tool you know till now, again I would say just try to apply it here. We have, you see, we have incorporated the constraint part as well within the objective function. That is why without any substitution, that is why even the constraint is a complicated in nature, that we need not to bother about it, because we need not to do any simplification. Just we will introduce one lambda there and we will just put it at the end of the objective function. We will append it there. Now, it will become again an unconstrained optimization problem. Again I would say, for an unconstrained optimization problem, if the function is twice differentiable, then the best way to handle it, go for the first order derivative, grad of the function, Lagrange function equate to 0, get the stationary points, then after that find out the Hessian matrix and see the nature of the Hessian matrix, and from the nature of the Hessian matrix try to calculate the optimal solution. That is the simplest way again. That is why in the Lagrange function you see there are few things, one is the function, one is the parameter. Just remember it, because you may ask me why I have deliberately we are introducing one parameter and it has no meaning of it. It is not like that. This is the necessary condition through the Lagrange, because since it has now three variables, now we can say that del L by del x1 must be is equal to del f by del x1 plus lambda into del g by del x1. B is a constant for us, that is why that part will not come. Alright. Now, del L by del x2 must be is equal to del f by del x2 plus lambda into del g by del x2. But from the third constraint, del L by del lambda equal to 0, you see we are getting the original constraint, but that should not be 0, that must be is equal to b. Alright. G x1 x2 must be is equal to b from the Lagrange function. If we consider b as a 0, then only it will become. Alright. That is why let us see one example for applying this method. You see we are getting just now we are landing to a situation where the situation is simple, but you see objective function is having a nonlinear function, constraint is also having a nonlinear function. That is why we will see how we can handle through the Lagrange multiplier. Now, one thing you see, if we just do this direct substitution here, we may face difficulty. Alright. May face, may not face, because y square can be substituted with x square. Nicely we can do for this problem otherwise. Now, for this problem let us apply the Lagrange multiplier method. Let us formulate the Lagrange function after introducing the Lagrange multiplier. Since there is only one constraint, we are introducing one Lagrange multiplier. If we have two constraints, we will introduce two Lagrange multiplier. Okay. Now, you see this is the thing. Now, we can go for the necessary conditions, just do the calculations to get the necessary conditions. We will get this thing. What you have? You have three equations with three unknowns, is it not? From here, can you find out the values of x, y, lambda? we can very easily we can find it out. That's a task of yours. I need not to do it, but you will get, we can do certain simplification from here, and from here we will get one relation between x and y. We can say at optimal point this relation will hold, alright. That is why we can declare one extreme point could be this one from the relation. Okay. We can have another extreme point as well. Now, if you want to check in the individual extreme points whether it has maximum or it has minimum, you need to do the, you need to calculate the, you need to see the property of the Hessian matrix, alright. That part you should do to get the sufficient condition. This I am keeping as an assignment to you. Okay. Do it on your own, find out the Hessian matrix, find out the principal minors, or you can go for the eigenvalues, calculate the thing and just to check whether this extreme points is a minimum value or not, alright. And with that I am concluding today, and in the next class we will deal with the Lagrange method for multidimensional cases, where we will have several constraints, okay, and together all are of equality type, and we will see the Lagrange multiplier method there. Thank you very much for today.